Okay, so let's start. Last time what we were looking at is the following, okay, is that in any undirected graph, the statement that we wanted to prove was the following: given a graph G and an integer k, okay, either G has k vertex disjoint cycles, or there exist alpha k log k vertices that covers all cycles, okay, or rather which is also called feedback vertex. Okay, I think I will have to better use my own pen. मेरा 20 रुपया. Okay, I think this is better. Okay. So towards that, what did we prove? The first thing that we proved, there was some number here, right? That, so one lemma that we proved last time was following: if G is a cubic multi-graph, okay, with at least sk vertices, right, with at least sk vertices, where sk is this function, okay, then G has k vertex disjoint cycles. Okay, is that fine? Right. So now we are going to prove this theorem. What is this alpha k log k? So we are going to prove this theorem, right? So we are going to prove this theorem with the bound will be, what will be used bound as let's say some ceiling floor, okay. So sk plus k minus 1. So this is where we are going to prove the bounds to be. And how did the proof go? So the proof, we literally saw the proof last time, but let's repeat it for the purposes of, okay. So what did we do? So we saw that, so the proof went, let H be an edge maximal subgraph of G. Let H be an edge maximal subgraph of G, where every vertex has degree either 2 or 3. Is that fine? Right? So let H be an edge maximal graph where every vertex has where every vertex has degree either 2 or 3. Okay, and now and we know that this H exists if G has a cycle, right? Because we could start with a cycle which is a degree 2 subgraph, and we could greedily try to add this until we cannot add anymore, meaning the moment I add any other edge to this subgraph, we lose the condition of degree. You get my point? Anything else, this is what I mean by edge maximal subgraph, right? And how can we achieve this is like, as I told you, this greedy algorithm, right? You compute cycle first, right? Delete them from your graph, and then you try to connect them via degree 2 paths which does not contain either of them, right? If it contains an edge, you put that edge, and like those vertices are marked. Okay. Now so such a subgraph exists, and we can greedily find, or for the proof, for the purpose of this proof, it is not important that how you can find this edge. It is just that such a subgraph exists. Now take any edge which you cannot add any further edges. Okay. 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 Now what we said is that let U be, so let this H, it's some, let U be set of vertices in V of H that has degree 3. Okay. Okay. So this is the first thing we observe. Okay. Now we consider what? Okay. So this is our potential set of FVS vertices. So like if G is a, like, so we have to come up with a, say there exists a set S of size at most this with this property. Okay. This is, so now we are trying to construct this S. Okay. So first of all, so let's, okay, so look at S which we want to construct. We will keep adding S something. So at this time what we added U to S. We will add some more vertices to S. Okay. Okay. Now what else other vertices we would like to add? Notice that degree of every other vertex in V of H minus U is 2. Okay. Now I am saying okay, okay. Now let's look at G minus U, okay, and I am going to call a vertex, call this set W VH minus U, because it's possible that my V of H is not equal to V of G, right? It's possible, right? For example, I have a cycle and like everything is flying around, right? Then the only unique subgraph is this degree 2 cycle because everything else is flying around, right? So it is possible that V of H is not equal to V of J. Okay. Okay. So now I'm going to call, okay, okay, a vertex X in V of H or a vertex X element of W is called interesting. It's called interesting if there exists a cycle passing through X in G minus U. I'm going to call this vertex X interesting if there exists, so it's a degree 2 vertex in my H, and I'm going to call this vertex interesting if there exists a cycle passing through X in G minus U. So you delete U from this, okay. First of all, observe that the way we have constructed vertex set of H is a FVS, right, because you cannot have any cycle outside vertex set of H, right, otherwise we would have added this cycle to our H maximality. So vertex set of H including 2 and 3 does form a feedback vertex set, but it could be of too large size, so we do not want that. But okay, so this is why I'm just trying to concentrate on X in G. So I decided that U is going to be part of the feedback vertex. So let's just forget those vertices by deleting them, and let's concentrate on the graph which is G minus U. Okay, in that I'm saying I know that these vertices of W is an FBS. I'm going to call this a vertex of W an interesting vertex if there is indeed some cycle passing through it, right? Now it's called interesting if there is a cycle. Okay, so I'm going to assign a cycle Cx arbitrarily to X. Okay, so I'm assigning some cycle. Okay, so now suppose I have an interesting set of cycles. Say I have interesting vertices x1, x2, dot 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 xl. These are interesting vertices. Okay, now for each of them I have assigned a cycle, right? Each of them, like arbitrary, which is a witness the fact that Yeah, this is interesting because here's a cycle. So this is Cx1, Cx2, Cxl. Okay. What is the property of Cx1 intersection Cx2? Can they intersect? My claim is for all I comma j,
No, they can't.
Cxi intersection Cxj equal to phi. They will never intersect. But H is an edge maximal degree 2, 3 subgraph. No, in H, not in G. I gave you just an example, no? Look at this, right? Make as many vertices, as many degrees of these guys, whatever you want. It is only this. It's in H. This is the only thing. Degree of every other vertex in this is 2 in H. Otherwise, it absolutely doesn't make sense, right? I mean, we are think about this. We are trying to prove this statement about any graph, right? You could come up with a graph with every vertex as degree at least 5. So think, right? We'll get there. That's a different thing. That's a different question. What happens if they do intersect? Okay. I mean, it could also be like, it's not like this. Okay, no, this is a bad drawing. Because I know x1 and x2 are distinct vertices, so they will start somewhere.
Can't they be part of the same cycle? I mean, can Cx1 and Cx2 be equal?
No.
Why can't they be equal? Because they, x1 and x2 are interesting, so they.
Yeah,
could be
you're
part
right.
of the
They could also be same. So what happens? I am not saying that they can't be. Yeah. Suppose this is a cycle. Okay. Let me start my journey from x1. Okay. I start my journey from x1. This is a cycle, so I can start my journey from x1. I start my journey and I look at. So first of all, notice that what vertices of H this cycle is going to contain? Only degree 2 vertices of H. Right? It may not contain any vertex of H for all that you know. Okay. So I start my journey at x1. Okay. And I take this journey via, I ask myself, okay, is this vertex that I am taking my journey is in W or not in W? Okay. If it is in W, what happened? Then these two vertices are degree 2 vertex. Okay, why did I not add this edge? Because then H, these two vertices will have degree 3 and it would not contradict the fact that H is an edge maximal. It will, okay. So fine, this is in where? So suppose this is in, this is why I said to you, right? Okay. So this is in Vg minus Vh. Okay. Keep on doing this. Okay. Keep on doing this, right? You will somewhere hit this red cycle, no? Right? It could hit the somewhere. First time you hit this red cycle. Okay. Where is this vertex? Yeah. Now, if either this vertex also, this vertex belongs to W, then you have found this. Okay. But otherwise, after this, I will start moving on the red cycle, which contains x2. Up until now, you did not look, because all this path I started from this x1. Where was this path? all this path is in Vg minus Vh. Okay, so I encountered the first vertex on the red cycle. Now I'm saying, now forget the blue cycle, just go on the red cycle. Okay, I go on the red cycle. Okay, finally where I will reach? Somewhere I will have to reach x2, no? Right? So if I reach x2 at any point of time, if I reach a vertex in W, I have got a path with every vertex is outside degree 2, end vertices also had degree 2. If I add this path, then these two vertices will have degree 3, and I have increased the size of my H, contradicting the fact that you cannot add any subset of H to my H and increase it. Okay, so what happens? So I go encounter, ultimately at least I will encounter x2 because there is an x2. So there is, so what did I encounter? So what is my, if I have a 2 cycle, then what is my outcome? My outcome is, then there exists a cycle, there exists a path between x1 and y, where x1 is in W, y is in W, and every other internal vertices on P belong to Vg minus Vh. This is exactly what I showed. Okay. Now what does this imply? This implies H plus P, H, and I add this path P to my H. H plus P is a degree 2 and 3 subgraph of size larger than H, contradicting that H is edge maximal. Is that fine? Okay. Right? So they are pairwise disjoint. Okay. So we have, okay. So I am going to add, so what does this implies? That if L is more than K, then I do contain K vertex disjoint cycle and I am happy. Otherwise, what is this? L is less than equal to K minus 1. Okay. Now look at the graph look at H as a graph. It could have several components. Right? It could have several components. So there are some components that do contain a degree 3 vertex, and there are some components that do not contain a degree 2 vertices. How many such components can be there? These are components of H. Okay. Now look, because how are we making? It's possible that all I give you is degree 2 things, right? So notice this is something which is x1 to xl is for the vertices of degree 2 vertices, which is from this, right? But it is possible that I have a cycle in H and that's my component, right? I may not be able to hit him because it has no vertex from outside, like there is no cycle which is hanging like this. It could be, right? So there are some components in H. Okay. So look at components of H. Components of H that are cycles. How many such components of H can be there? And look, in fact, I'm going to call this component is like, this component is only important if you do not have an interesting vertex on this. But I forget, I don't care about it. I will increase by something. Okay. But how many such cycles can you get? How many such components can you get? At most K minus 1. Otherwise, again you have K vertex disjoint cycles. Okay. So number of such components are upper bounded by how much? At most K minus 1, else we are done. Okay. So in this case also I said just pick up one vertex from each of this cycle and you are happy. Okay. Let's call this set Z. So now our S became S became U union x1 to xl interesting vertices union I picked up some set z. Okay. Now they have some size up until now. Okay. Now my claim is that in fact, so S is a FVS claim. S is FVS. If I prove this, I'm done. Why? Because then all I need to care about is the size of U should be bounded, which I will show you in a minute. Okay. But let me at least claim that the S which I have constructed is an FVS. Is that fine? Okay. But why is the current S FVS? We knew that V of H is an FVS. Okay. So after I deleted all this, I'm going to get some cycle. But that cycle must contain a degree 2 vertex. Right? That cycle must contain a degree 2 vertex. Right? After I have deleted S, right, I knew that every vertex is like, again you look at this vertex, right. Now is it possible that this vertex, it means is this cycle just hanging around on them? What did we make? This vertex was interesting if there was some cycle on him. This is exactly what I said, right. So after I have deleted this, can there be a cycle on, because now I have deleted interesting vertices, I have deleted those vertices, everything. Okay. Now look at this. Can you have any cycle at all? First imagine that there were no components of those nature. Can you have? Because otherwise why was that vertex not marked as interesting vertex? Is that clear? Right? So it is indeed true that S is my feedback vertex set. Size I am not talking about, but like all I am trying to tell you at this point of time that S is FVA. And why I am saying, okay, you delete degree 3 vertices. Okay. Now look at Erdos components. If it is a cycle component, now you can ask, right? Oh, okay. You can ask that why can't I have a degree 3 vertices here in this component? But if there is a degree 3 vertex on this component, right, then that will anyway take care by W, take care by U. Okay, so all of you look very confused. Okay, so let's look at this S and look at G minus S. Okay, look at G minus S. And suppose there is a cycle here. Okay, where are these cycles? Definitely it doesn't contain any vertex from S. So what does it contain? It contains a vertex V. Okay, it contains a vertex V. Okay, it contains a vertex V in vertex set of H minus vertex set of H minus U and everything else that we selected. Okay, and but look at this cycle. This cycle also cannot belong to G minus U. Why it cannot belong to G minus U? Because then this vertex is an interesting vertex. That should have been picked up here. What did I say? Look at x1. I said a vertex is interesting if there exists some cycle that contains x1. This is my definition, right? I said a vertex is interesting if there exists a cycle passing through x in G minus 1, G minus U, right? So if I delete S, I have definitely deleted every vertex in U, right? I still got some cycle, right? So we also know that V of H is a FVS, right? It means this cycle, it contains some vertex V in V of H minus U, right? And so if this cycle was in G minus U, if this cycle was in G minus U, right? If this cycle was in G minus U, then this is an interesting cycle. So this cycle does not exist in G minus U, right? So this cycle does not exist in G minus U, right? This cycle does not exist in G minus U minus interesting vertices. This does not exist. So where is this cycle? Where is this cycle? Huh? But then, so only place this cycle could be, the only place this cycle could be that it must contain some, okay, so this cycle could be, the only place this cycle could be is that this cycle actually belongs to H. Okay, or let's say, okay.
Even if it belongs to H and it contains some vertices of this.
So we'll get there. Okay, so at least this much is clear that this cycle is not contained inside here. Okay, now here is your W vertices. Okay, sorry, here is your U vertices and here is your W vertices. Okay, you know, and this is your remaining graph. This is my remaining graph. Okay, what do I know about this? This cycle is not here. This cycle is not here. In fact, this cycle is not here. This cycle doesn't belong here, because if this cycle belonged here, then we would have picked it up because of our interesting cycle property. If this cycle is here, it will contain some vertex of V of H, right? So this is like, so this cycle does not belong here. Okay, and so where is this cycle? Okay, huh? It contains vertices from, it could be like this cycle, right?
Yeah, but it contains vertices from U but not from W.
It contains vertices from
U and the rest of the graph, but it does not contain vertices from W.
But then U is anyway part of your FVS, no?
So that means
What does that mean?
it does not exist.
That's it. Yes. So you can argue step by step that this is indeed an FVS. That's all that I'm trying to do. I was not doing anything more magical. You draw this cycle, I say where did this cycle go, right? In fact, the way I define, I don't even need to do this, notice, right? Because I'm telling you that even these kind of components are interesting components, right? Because I would have marked them as interesting components, interesting cycles, so anyway they are pairwise disjoint. So in fact, I don't even need, if you notice, because of my definition, I don't need Z. Interesting is more than enough, right? Because if this cycle is not contained inside this, then where is this cycle, right? Its cycle must contain this vertex. If this contains, that's anyway FVS. So you're done. Okay. So what did we saw then? What is the size of S? Size of S is less than equal to U plus K minus 1. Okay. Now let's focus on U. Is this fine? Okay. So the crux of the argument was that this is a very beautiful structure. Now look at H. Okay. Look at H. Okay. What is H? Is degree 2, 3 subgraph. Okay. Now notice, so now look at H and look at components C1, C2, CL. These are like components of this. I call a component C1 heavy if Ci has a vertex of degree 3. Then this is a heavy component. Okay. Now look at C1 to CL, which is not heavy component, means every vertex is degree 2. It means that's a cycle. right? So let's not worry, because anyway those cycles do not exist anymore, because those cycles are anyway taken care by my interesting set, so we will not worry about those. So let's only worry about, so our U vertices belong to which component? Only some, so these are the components that contains our degree 3 vertices. Let's focus on those. Let's focus only on those components that do contain a degree 3 vertices. Now, what is the property of this graph? Is 2 and 3 vertices, right? This. Now, all I wanted is to upper bound the size of U. Okay. So what I'm saying, now I'm saying, look at H, obtain H hat by suppressing degree 2 vertices, right? Because what I mean by suppressing degree 2 vertices, if there are degree 2 vertices, any cycle that pass, I mean, what I mean, let's don't worry about this. Look at this. What's the property? Any cycle that goes here comes out from this way. Okay. So what I'm saying, let's forget this degree 2 vertices. Let's add an edge between them. Let's delete this vertex. So what is an operation? X, Y, Z, delete Z and make X and Y adjacent. That's it. Okay. It could create a multiple edges, right? So I am going to get this structure X, Y if there is no edge between X and Y. If there would have been edge, I get X, Y. But notice the degree of X and degree of Y do not change. That's important point. Okay. So after we have done this suppressing of degree 2 vertices, what is the property of H tilde?
Everything will be degree 3.
Everything. And this is where we use the fact, that we are only going to do for C1 to CQ. Because if the component would have been, every vertex would have been degree 2, what will happen? You are going to get a cycle. At the end, a single point and self loop, right? Because if this is the operation I'm going to do, imagine a cycle. What will this operation can do? It can't make look, this is a degree preserving operation. Can it create a degree 3 here? So if you had at least one degree 3 vertices, it can give you a degree, it can, at the end, it will result in a H where every vertex has degree 3. But if the start with you do not have any degree 2 vertex, you cannot do anything. And that is why we do not apply these operations on those components which are just degree 2, because that is never going to result in a degree 3 instance or a multigraph of degree 3, right? So this is why we are doing this operation only on H tilde, basically H C1 to CQ gives us H tilde by suppressing. Okay. So this is why we have to distinguish between them, because look at the example which I drew. I will get just a cycle. Can you make that degree 3 by contraction of this? But if a component has a degree 3 vertex, I can always do it. Okay. So now what is the property of H tilde? Okay. Now H tilde. What are we? Now suppose size of H tilde is large. Is larger than SK. Then what do I know about this? That H tilde K vertex disjoint cycle in H tilde. Okay. Now we have to go back. Look at an edge here. It's possible, like go one step by one step, right? Look at a cycle here. Maybe you have an edge here, but actually this edge has been obtained by taking a vertex and suppressing a degree 2 vertex. Okay. But now what you do, I am saying now do the unsuppress operation. What is the property of unsuppress operation? even after unseparating, these cycles remain vertex disjoint. Okay. So what is the meaning? After unseparating operation, I am going to get, so suppose I have got cycle C2 Ck hat. What I am going to get here? I am going to get here C1 C2 Ck, right. So the moment you do unseparating operation, if you had a k vertex disjoint cycle in H hat, this will result in a k vertex disjoint cycle in H C1 to Ck, which means these are k vertex disjoint cycle in G itself. Okay, then we have. Otherwise, what you know, if this does not happen, it implies that H hat is bounded by Sk. But what is the size of H hat? It's precisely U. What is the property of C1 to Cq? These are those components that contains by degree 3 vertices. These operations does not change the degree. So the vertices which had degree 3 to start with, they will remain degree 3 in this operation, and you are not going to create any more degree 2 vertex, any more degree 3 vertices. Okay. So in fact, this is exactly equal to U equal to H hat or vertex set of H hat, whatever you want, and this is less than equal to Sk. Okay. Now we have our upper bound on U. So what does this process tells us? Either in this process we are able to find k vertex disjoint cycles, or we are able to show a FVS of size how much? What is size of S then? Size of S is upper bounded by Sk plus k minus 1. So whatever, so this is something, so of course this is, so this implies that this is bounded by Sk plus k minus 1, because this is an integer. So if something is less than 2.3, then it is less than equal to 2. That's it. Is that fine? Ajay, you look very confused. What was my goal? My goal was to upper bound size of U, right. So to do that, I constructed a graph where just U survives. That was my H tilde. Okay, this H tilde. Why H hat? I don't know. Sorry. Okay, H tilde. Okay. Now that's only thing survived. Now we said if the size of, what is the property of H tilde? It is a cubic multigraph. So now I can throw up my theorem, which says if the size of this is too large, you have k vertex disjoint cycle. Now if that is a k vertex disjoint cycle, that implies that graph G, original graph G, has k vertex disjoint cycle, right? By unseparating operation, which implies that if the graph we started with does not have k vertex disjoint cycle, it means what is the size of H hat? Sk. Okay. So now what is the size of U bound? So what is the size of S bounded by? Cardinality of U plus k minus 1, right? Because k minus 1 was those interesting vertices that we picked on the way, right? Those were anyway small. It's just that in the beginning when we computed this degree 2, 3 subgraph, those were contributing to the weight, like those were contributing to a lot, and we said don't worry about it. If they are too many in this process, then you already have k vertex disjoint cycle, and if they are few, then anyway you have got a feedback vertex set of small size, which is like roughly k log k. So that's what is happening. Okay, this theorem is very amazingly powerful, and like, okay, so this theorem has like amazing ramifications. Okay, in the sense that a lot of new tools have been developed in last 3-4 years. Okay, So for
Tools mean?
I'll tell you in a minute. Okay. Imagine I'll get there. Suppose I give you this. You see? This 2x2 grid. Okay. I said my graph contains a subdivision of 2x2 if you can identify some vertices in your graph like this, which will map to these guys, right? These guys. Okay. And for edges, you are allowed to use any path, but they should be internally vertex disjoint paths. Okay. You get my point? I said, look at this model. Can I realize this model in my graph? So I say that this model can be realized in my graph if for each of these vertices I assign normal vertices in my graph. Okay. And for each edge, you are allowed to associate a path. But what is the property? So suppose for this edge E1 you associated a path P1, E2, PE2, so on and so forth. Their property need to be that they should be vertex disjoint internally. Okay. So this is called model of this. Okay. So now if I ask you, if my question was, can I delete k? So either I want to say that either there exist k models of this object in my graph, so which means I can like there is a partition of vertex sets where each of them contains this model, okay, or I can find some set of vertices that such models do not exist. Okay, right? Okay. Now let's look at the model for cycles. What is the model for cycle? This is it, triangle. Triangle. Any cycle can be modeled like this. Look at graph, right? Because I assign any 3 vertex, and for each of them you assign vertex disjoint path. So if I look at this regime of things, okay, then this is just a triangle. Okay. Now I can come up with any family H and cycles, set of and some graph H1, H2, HL, and I say, look, either my graph has for any number k, I can partition my vertex set into k parts such that each of this piece contains model of one of these guys, or it contains none. Okay, or it contains none. Okay. Now the question is, for which families of H such Erdos Posa holds, or which family of H this may not hold. Okay. You understand my question? So I give you some family of finite graphs. They are finite graphs because now for cycle we don't have to take all the cycles. I give you a triangle and say that is the model which you want to hit. And what is the definition of model? You look at this, you cannot assign vertex here, vertex here, vertex here, and paths between them like this. Okay. So that's like a cycle. Okay. So this is a very big study. Okay. And under some very nice theorem is that k log k is all that you need for the truth. Okay. Anything else? Otherwise we'll move to proving something else in next 40 minutes. Okay, something of this nature.
One thing, so the definition of edge. So we are taking a subgraph where every vertex is degree 2 or 3. I understand why we want degree 2 vertices, but like, what is the significance of degree 3 vertices? As in like,
In which, when we computed h in the previous proof.
no, not the proof, but like in the beginning.
Meaning
The definition of edge, right?
S.
Edge.
Definition of h was either degree 2 or 3 vertices.
But why degree 2 and degree 3? Like, you could also get degree 2, degree 3, degree 4.
You could.
Like, only degree 2 would end up meaning you have disjoint cycles.
Yeah.
Degree 3 would mean, okay, like if we consider a cycle and you pick any 2 points on the cycle, they might be joined by a path, another vertex disjoint path. Why degree 3?
But then you ended degree 3 here, no? I am not understanding what you like. I do not understand your question. Can you rephrase your question?
Why does the subgraph H need to have degree 3 vertices?
2 is not enough. You at least agree to that?
Yeah, 2 is not enough. But why do we end at degree 3 and not big?
Because 3 is enough. There are more subtle reasons for it, but we are not prepared for that reason yet. That's one thing. And B, as I told you very in the beginning, what is the property of this degree 3 subgraph? Like basically with respect to FVS, every vertex is good enough. That is the property of 3. In fact, this is true about 4 or 5, but every vertex has to be that almost that regular. Okay. Now, suppose I prove this for 4. Okay. But then, what theorem should I look? I told you in the very first day I told you, right, that I mean roughly degree 3 has a property that everything else should happen. Okay. Now, if I allow 3 and 4, what is the proof then? I can prove that okay. With respect to 4 I can prove, with respect to 5 I can prove, okay, but it starts becoming a bit more complicated, right, in the sense that, but you could use that. There's absolutely no reason to not use 3, 4, 5, use any of those things.
But like how do you figure out, let's say if you are trying to prove a theorem, how do you figure out when to stop, like when is it sufficient, when is it enough?
When it is enough. Experience. There is no, but no, look, there is a property, right? 3 regular graphs are like expanders, right? Why do I go to 4 and 5 and 6 make my life harder if I can do everything with 3, right? So, what is the property? The property, so basically what is the 3 regular graphs which gives us everything nice? They are basically what are called expanders. Expander means that if I take you any large side partition, there are far too many edges going across. And this is true about every partition, right? Why? Because if it is small number of edges going across, then I can pick up these things and that's good, left and right. You understand my point, right? But imagine yourself that if I have a large flow going on from here to here, I mean now I have to take lots of vertices in one side to disconnect both sides, right? So this is what is called expanders, right? What is the meaning of expanders? For any partition of my vertexes where both sides are sufficiently large, there are sufficiently large number of edges going across, okay? So for any graph family, those are the hard instance. But what does that mean in this case? If there are far too many edges going across, that also means that I can probably create far too many cycles, right? So if I can create far too many cycles, so expanders are great for me, right? Because with respect to Erdos Posa, expanders are great because in some sense I can create anything I desire in some sense on these expanders, okay? So another thing which is very, okay, all these are very much inherently related to tree width, okay, which I will come at the end of the course. So now what happens is that given any graph, if it has a huge tree width, then there exists a subgraph of degree 3 which inherits all its tree width. Okay. So all the difficulty of separation that general graph has, there is a subgraph which is cubic and that does all the job. So like the moment I move from 2 to 3, for several things in the world, 3 is as good as this. For example, you note vertex cover remains NP complete in 3 regular graphs itself, or graphs about degree at most 3, right? And it doesn't even have any sub-exponential algorithm. It does not even have a polynomial time approximation scheme. So its behavior is more like a general graph than graph classes like planar graph, right, which has like much better things in world. Why are these things? Because one has interesting ways to separate things, okay, other does not have, Okay. So this is basically the kind of separation properties. So now if I know that anything that I can do on 4, 5, 6 or 10, I can do it on 3, why should I go and do 4, 5, 6, 7 and 10? And let me do at 3. Like any theorem more or less you can prove for 4, 5, 6 of this nature, you should be able to prove it on 3 itself. Okay. So that's more meta reason. Okay. And in fact that will give you proof for everything. Okay. Okay. So let me okay. Okay, and now you see why you have a constant factor approximation. So in fact you can get a factor 4 approximation from this. Why? Because you can bound it by, so you have to be careful, but like you can bound by 4 times opt, and this is opt, so 5 opt is here. You can bound kernel of u by 4 times opt, optimum feedback vertex set, but what we saw is 6 times opt, so this will give you 7. And if you just do slightly careful analysis here, it will give, because these things which you, like they were different vertex disjoint cycles, so you have to anyway pick them. So for these kind of things you can associate different set of cycles and then you can get like 4 opt. Okay, but that's okay, but we'll not go there. Okay. Now I want to move to directed graphs, which I have never talked about in this class yet. So what is directed graph? Directed graph or directed graph? Okay. So what are directed graph? Directed graph D, I'm going to use G and H. Okay. But basically you have a direction from U to V from every pair of this thing. And some famous directed graphs are, for example, directed acyclic graph. And you must have studied in your school that, or in your undergrads, that a directed graph D is a DAG, directed acyclic graph. It means as a direction it does not have a cycle. For example, this is not a directed cycle. Okay. If I forget about arcs, there is a directed cycle. But if I do not forget about arcs, this is not a directed cycle. But this is a directed cycle. Okay. Okay. Is a DAG if and only if it is, if and only if it has a topological ordering. Okay, it is a topology. What is the meaning? It means you can come up with an ordering of vertices V1 to Vn, and what is the property? Look at any arc Vi Vj. Look at any arc Vi Vj. Okay, it is goes from a smaller index to a higher index. Okay, so this is why it is called topological ordering, and all the dynamic programming algorithm is done to topological ordering, right? You go from left to right, because so that whenever here all the sub problems or everything which has been done previously, like that depends on, has been done previously. So if you write a DP recurrence and look at the sub problems and draw a directed graph, if it is not a DAG, then your recurrence is just wrong. You can't do DP then, because if there is a dependency in it. So that's another. But okay, so a directed graph D is a DAG if it, but what is the property of DAG? It does not have directed cycle. If look at a sub problems and draw like there is a vertex for sub problems. If a sub problem depends on something else, then just like if this guy depends on the solution to this, just draw an arc from sub problem to this sub problem. Right? It must be DAG. That's it. If it is not a DAG, then there is something not right. Okay, so this is one, right? So now, isn't it a very interesting question that whatever theorem just be proved could also be true about okay, so what about the following theorem? Potential theorem. Okay, let G be a directed graph, let G be a directed graph and K be a positive integer, then either G has K vertex disjoint cycles, K vertex disjoint directed cycle. So now whenever I mean cycle, I mean directed cycle, okay? Or there exist some f of k vertices such that f of k vertices say S such that G minus S is a diagonal, right? So it's just a directed counterpart of whatever theorem we just now proved, okay? Or there are also an arc version of this question, does G has K arc disjoint directed cycle or f of k arcs say S so that G minus S is a diagonal, right? So you could ask either you have K vertex disjoint directed cycle or K arc disjoint directed cycles, or you can find some f of k set of arcs that if you delete, whatever remaining is a diagonal, right? So this is open for a long time, okay? But this statement is true, okay? But unfortunately this f of k, I don't know what it is huge, okay? Okay, okay, yes.
What is an arc again?
Arc is this is an arc, edge, directed edge. I just, you can think of that edge. Okay, if you want to think arc is set as edge. Okay, so at least giving a proof of this theorem is beyond the scope of this class and beyond the scope of most classes. But so I don't even know the proof. So to be very fair, I have tried to read this proof several times, but I don't think I ever got across. This is like, okay, but this is a one desire I have in my life, that maybe sometime I will see a proof of this which is simpler. Okay, so we'll focus our attention to what is called tournaments. So what are tournaments? It's a very interesting graph class. Okay, look at a complete graph, click, orient every arc, left, like anything. So what is a tournament? Is there are several definitions. Orientation of a complete graph. Okay, what is this? Orientation of a complete graph, right? Or it's a such that for each u cross v in v cross v, u not equal to v, either u to v is in E or v to u is in E, but not both. Okay, so whatever you want to say. So a tournament is basically like a tournament, right? Like, so you have n vertex and give me any pair u comma v. So either I will give you an arc from u to v or v to u. Okay, now this is a theorem which I want you to prove yourself, and I will prove the difficult one. Okay, so the theorem which I want you to prove, let T be a tournament and K be a positive integer. Okay, then either T has K vertex disjoint cycles, or there exist f of k vertices, say S such that G minus S is a DAG. Okay, So I want you to prove this theorem for me. Okay. What I am going to prove to you, let us say an arc version of this. Okay. So what I asked you is a very easy exercise, it is not very difficult. Okay. So now let T be a tournament, okay, and K be a positive integer. Okay. Then either T has K arc disjoint cycles, okay, arc disjoint cycles, or there exists a set S subset of E of T of size f of k such that T minus S is a DAG. Okay. So I am just going to prove. So what I have asked you to prove is a vertex version of this, and what I am going to prove is an arc version of this. Okay. Okay. So let me give you the difficult proof, not give you the easier proof. Okay, because it has better bound. There is no other reason. Okay. So I am saying to you, here is the lemma. Let D be triangle free. Okay. Let D be a triangle free digraph. Okay. And suppose number of non-adjacent pairs is this. What I mean by look at some UV, there is no arc between them, then I am going to call non-adjacent pairs. There could be many non-adjacent pairs, okay, but delta G is upper bounded by n choose 2. Okay. Then what I am going to call this set S, I am going to give it a name. It is called feedback arc set, and this also has a name. It is called directed feedback vertex set. Or okay, the way. Okay, then I am going to prove that then FAS of D is less than equal to this non-adjacent pairs. Okay. So what is my lemma? Lemma says let D be a triangle free directed graph, and suppose number of non-adjacent pairs is some delta D, then feedback arc set of D is at most delta D. What I am saying, then we can actually delete some set which is upper bounded by number of non-adjacent pairs, okay, and make the graph acyclic. Now why does lemma will imply the theorem? Let us see. First, do you see why lemma will imply the theorem?
Can we not use delta of T as our f of T function?
How? Look, T is a tournament. D is any directed graph, and there are some non-adjacent pairs. Okay, and what is the property? What is the non-adjacent pairs tells us that okay, if some delta of D are non-adjacent pairs, then there is a feedback arc set in this diagram which has this nice property. What? That is exactly my question, right? Like, how does this lemma imply this theorem? That's exactly my question.
Your triangle free means directed triangle.
Yes. That is precisely my question.
Non-adjacent pair of vertices in V would imply
That's just a bound.
So in this tournament, like, consider maximal subgraph which doesn't contain triangle.
What?
Partition into triangle.
What are to say?
In tournament, you consider a maximal subgraph which doesn't contain a triangle. Then use this step somehow.
Or maybe do something else, no? Why? Triangles are not cycles? Then do some greedy, no? What's the big deal about it? Okay. Here's my tease tournament. Let Q1 be a triangle. Okay, directed if there exists one. Okay, otherwise we'll do something about it. Okay, okay, and then arcs. Okay, let Q2 be a triangle in T minus Q1. Again, as a set of arcs, I am going to delete. Like, please understand by context that Q1 means I am just deleting set of arcs. I do this. Okay, I do this and I get Q1, Q2, QL. How many times should I get this? L is upper bounded by? Otherwise, L is at most K. Else you are done. Okay. So now look at all these set of arcs. Okay. Now let A is union of Qi I equal to 1 to L. How much is the size of A? Okay. What is the property of T minus A? Is it a triangle free? Is T minus A triangle free? How many non-adjacent pairs are there? Huh? Pairs in T prime? Huh? How many non-adjacent pairs are there in T prime? Huh?
at least the number of edges you will.
But T was a tournament. Is at least or at most?
At most 3k minus.
Why? Because T had every arc possible. Now, only thing which is missing is what we deleted it, right? So, delta of T prime is less than equal to 3 times K minus 1. Okay. So, what is my lemma tells us? There exists a set S subset of E of T prime such that G of T prime minus S is a DAG. Okay. So, what is my feedback arc set? Is S union A. Right? You first delete A and then you delete S. What is the size of this? This is less than equal to you're done. So if we have this lemma, this proof of this theorem is easy. Okay. Assuming this lemma. So all that matters is this combinatorial lemma that we need to prove, which has nothing to do with tournament. Is that fine?
So why is the size of f less than 6k minus 1? That was 3k minus 1.
There's a S, there's a Q, there's a A also that we picked up, no? How did I get to T prime first? First I deleted some set of arcs. How much was there? There were,
That was 3k minus 1.
and now in T prime, who knows that T prime does not have directed triangles. That doesn't mean that it does not have cycles.
So how do we know that it is exactly less than or equal to 3 into k minus 1?
What is the theorem statement?
Says that the number of non-adjacent, it is less than the number of non-adjacent pairs. So why should the number of non-adjacent pairs be less than or equal to 3k minus 1?
Please apply brain, no? Either you are not reading the statement. Please read the statement, no? I just answered that question 2 minutes back. That is the definition of tournament. Read the definition of tournament, no?
Yes, sir, I already have it. I mean, I understood what is it for.
So if from some to, so how many non-adjacent pairs are there in tournament?
0.
0. So how many non-adjacent pairs can you create by deleting some arcs?
Exactly the number of.
So that is exactly what it is upper bounded by A, no?
So we deleted 3 into k minus 1, but how did it become 6 into k minus 1?
Because size of F became S union A, because I'm talking about feedback set of tournament. I'm not talking about S is a feedback vertex feedback arc set of T prime. There exists a set S subset of E of T prime such that T prime minus S is a DAG. What is the size of this S?
That's what I'm not able to. So size of S is less than or equal to delta of D.
Which is at most? Size of S is less than equal to delta of T prime, which is equal to, which is upper bounded by? How many arcs did you delete? What is T prime? By definition is T minus A, which is, okay, which is this, which is at most 3 times k minus 1. Okay, there is nothing happening in this theorem, absolutely nothing. Okay, all the magic is hidden here. Okay, so let's try to prove this magic. Okay, let's see. It works, but don't ask like why and how. It is just like I have no answer to that question. Okay, this is something just like by trying it came. It's not that I have a very clear picture that why does it work. I just heard some talk somewhere, like, and then from there it is. So I personally I have no intuition. So sometimes you prove something, it does not need, it doesn't mean that you have intuition for this. You understand my point? It is like some chain of thoughts that you start from somewhere that takes you somewhere and that takes you somewhere and that, but doesn't mean that you saw that that is where I want to reach. You understand my point? Like one started somewhere else and you suddenly find some structure and say, oh, that structure can be used, and then you make that a structure as a statement. Okay, so this is a very different way of doing things. Okay. Okay. So first, what I'm going to do, I can let's look at a D, right? Okay. Okay. So all I had to care about is this. So first, I'm going to do some pre-processing to D. If there is a vertex which is either source or a sink, can there be any directed cycle passing through them? Okay. So if all the vertices are out neighbors or all the vertices are in neighbors, these vertices are completely useless for our purposes. Okay. So here is just some pre-processing that I would like to do. So what's the pre-processing? Okay. no source and no sinks. Source means in neighborhood of V is 0. Sink means n plus of V is 0. So what is n? In neighbor. And what is in neighbor? These are called in neighbor of vertex. Okay. And what is out neighbor? These are called out neighbor, like vertex which it can reach by directed arc. And what are in neighbors? Those vertices that can reach me by an in arc. Okay. So these are also called in arcs, those are called out arcs, these are called in neighbors, these are called out neighbors. Okay. Okay, so we can do this processing. But notice by doing this pre-processing, I have not changed the feedback arc set. I might have decreased the number of non-adjacent pairs. Then so be it. Right. I mean, if I can show that my feedback vertex set in this graph is upper bounded by non-adjacent pair here, it also implies that they are upper bounded by non-adjacent pairs in the origin. Because by deleting a vertex, you might have decreased the number of non-adjacent pairs. You can never increase the non-adjacent pairs. Right. So from D, I get to D prime. Okay. And what is the property of this? The first property is feedback arc set of D is equal to feedback arc set of D prime. That's one thing. And delta of D prime is less than equal to delta of D. Okay. These two properties, which implies that this theorem I will prove is that FAS of D, which is equal to FAS of D prime, is less than equal to this, right, which is less than equal to this, and then we are happy. Okay. So we can assume that we have a pre-processed graph. Okay. We have a pre-processed graph. So step 1, pre-process D, so that it is important, so that every vertex has in neighbor and an out neighbor. That's it. So this is what I have done up until now. Okay. And another thing we will do is that we are going to prove this by induction on. So okay, I should have told this. We are going to prove this by induction on vertex set of D. Okay. Induction. So if D equal to 2, this is perfectly correct, no? If the vertex set of D equal to 2, I want to do induction on vertex set of D. So imagine that vertex set of D is equal to 2. There is no cycle, or if there is a directed cycle, is like the worst case like this, right? In the worst case it is like this. So I can definitely delete. So I think we should assume that is an oriented digraph. Okay. So we are not allowing these kind of cycles, otherwise we can't prove this, right? Because there are no non-adjacent pairs at this point of time. So otherwise, what is the definition of non-adjacent pair? So what is the point? So this is something you have to assume, that this kind of directed graph are called oriented digraph. Okay. So this statement is only true about oriented digraph. It means between any pair of vertex there is at most one arc present, either U to V or V to U or none. Okay. Not like this kind of multi-circle. Now it is okay, right? Because now it's 0, right? Feedback arc set is 0 and so is non-adjacent. So this is perfectly fine. Okay. So this is base case. Okay. So I should have started from here and then gone here, because if then I find this vertex, I delete it by induction hypothesis, we are done here, right? Because I have deleted a vertex, right? So I start with base case and then I will see if there exists a vertex V which is source or sink, delete it, number of vertices are decreased by induction hypothesis, it has this property, we are done. Okay. Okay. So okay. Okay, so this is a definition which is bit not nice. Okay. So what I'm going to define, first of V. What is first of V? Okay. So it is number of induced paths of length 3, number of induced paths of length 3 in which V appears as first vertex. Okay. So, what is an induced path? Induced path means this is an induced path, but there are no arcs. This should not be, otherwise it's not an induced path, right? Induced path means x, y, z is an induced path. Okay, is an induced path if no arc between x, z. But what about this? Like you do not have this, but what about zx? So you don't even have such things, right? This is why I use, that's a triangle free diagram. That's a place where I will go to. If you have an induced path like such that xz is not an arc, then you definitely do not have zx as an arc, because this is a triangle free rectangle. Okay. So you understood the definition of first of V is number of induced paths of length 3. So like with 3 vertices in which V appears as first vertex. Okay. So I'm going to define middle of V. Okay. Same definition, but number of induced paths of length 3 in which V appears as second vertex or the middle vertex, second middle vertex. Is that fine? Okay. Let me see if how many of you believe this claim. Okay. Summation over V in Vd. Okay. First of V is a number is equal to summation V in Vd middle of V. You consider any induced path UVW, right? It contributes, this path P is going to contribute what to what? This path P is going to contribute 1 to first, and this is going to contribute 1 to first of exactly one vertex, right? And it is going to contribute, right? So it is going to contribute first of only U. It cannot contribute first of any other vertices, right? So, okay. What about middle vertex? Right? This guy is going to contribute middle of one vertex. It is not going to contribute to middle of any other vertex. You fix a path P, right? Now you ask yourself, like, what is their contribution? So definitely this guy only contributes in the first of V. So if look at all induced paths of length 3, all in your graph, all, right? Now look at the first, look at, these are distinct paths. Look at this particular path. This particular path is going to contribute to first of exactly this guy. It cannot contribute first of anybody else because, because of the starting vertex. Now look at the middle guy. Can this path contribute to middle of two paths? Two different vertex? No, because this is unique middle. Because we are going over all paths. we are counting over all paths. I am not segregating any path. I write down all the paths, right? I write down all the paths, right? So now what is this? Okay, so this is going to contribute to one of first of this is going to contribute to middle of V. So you write, no? So suppose you have a first of some vertex, middle of, like, okay, so let's say how, here is the first counter, here is the middle counter, okay, V1, V2, Vn, right? Look at this path, it's going to contribute what? 1, 1, right? Look at the second path, it is going to contribute 1 to this, 1 to this, right? So every time you pick up a path, that path contributes 1 to both counters. What does that mean? If it contributes 1 to the both counter, it means the sum of the counters here is equal to the sum of the counters here, right? I went through each of the path. I went to the first path, what happened? It contributed 1, 1 to both. Now second one, oh, you are first of him, so let's go and contribute here. Oh, but then you are middle of him also, so let me go and contribute. So middle will contribute to somewhere else, not to the same place, because U and V. So this guy is going to contribute first here and middle of some other vertex. But at the end of that, whenever you made change 1 here, you also making change in this column, right? So that's all that matters. So if I started with all 0 values, so now think of this as the coordinates, no, right? So whenever, so you started with all 0 vectors, first path came, it changed the coordinate by +1 in the first vector, it also changed the coordinate by some coordinate by +1 in the second vector. That's it. So this is exactly what.
We can also say that this is equal to the number of induced paths of length.
Number of, yeah, this is true actually. Number of,
We,
yes,
enumerate based on that.
correct, 100% sure. This is exactly what it is. Okay. Okay, what can we say? There exists a vertex U. This implies there exists, we will spend some 10 minutes, okay? Because I don't want to do this proof again next time, otherwise it will just go flash out of my head. There exists a vertex U such that first of U is less than equal to middle of U. Do you agree to this? Look at this sum, no? For every vertex, how is it possible that first is greater than its middle? Is it possible? Because they are equal, no? There exists a vertex U such that first of U is less than equal to middle. Suppose this is not true. Then first of U is strictly greater than middle of U for each U. Now sum them, no? You said they are equal. This is just a Pizarro principle. There is nothing more happening. Okay. Okay. This is fine. And this is where we will define our whole. Okay. I pick up a vertex U. Okay. I write set UU. What is this? These are n minus of U. Okay. In neighbors of U is this set. This is n plus of U, and here it is R of U. Okay. In neighbor of U, out neighbor of U, remaining vertex of U. Right. So neither they are in neighbors or out neighbors. Okay, excellent. Now, if you look at the picture, right? Nothing here. I'm not saying anything about this and this. All I'm saying to you is this. Okay? Okay. What can you say about n plus u? Are there arc here? Are there arc here? No, because then you will get a directed triangle. We are talking about triangle free diagonal. Use the fact. Okay, excellent. Okay, okay. Now what I'm going to do, there are some things you should observe. Yu is not equal to phi. Why? Because this we did pre-processing. Out of u is not equal to phi because we did pre-processing, because if there exists a source or a sink, we deleted it, which means every vertex has some in neighbor and some out neighbor. Okay, so this set, because otherwise how will we do induction? Okay. Okay, so what is my D1? D1 is a D induced on RU union this. Okay, this is my, and what is my D2? D times out of U. This is my D1 and D2. Okay, notice there is a property of, what is the property of D1 and D2? D1 and D2 contain strictly less vertices than D, because this is not empty, this is not empty, which implies that D1 is strictly less than D, D2 strictly less than D. Why do I need this? Because I can apply induction on these things. That is my whole goal. Okay.
So here what is D? What is D?
D was my directed graph started with, no? So D induced on this, D induced on that. Okay. So what is my goal? Okay. What is my goal? Okay. So let me say what I wanted to do, what I want to do. By induction hypothesis, I can say, right, what does induction hypothesis tells us? Induction hypothesis will tell us that, look, feedback arc set of D1 is less than equal to delta of D1. Feedback arc set of D2 is less than equal to delta of D2, right? So this will imply that every directed cycle that contains inside here is taken care of. Every directed cycle that is here has been taken care of. Okay, fine. Okay, but there are cycles which is going across here. I need to do something about them also, no? Right? And that shouldn't be more, because we have to show that those has to be less than equal to delta D. So I need to show that, hey guys, you still have lots of, look at the non-adjacent pairs, right? So non-adjacent pairs here are also non-adjacent pair in the original digraph. Non-adjacent pairs here is also present in, so those are fine. But in fact, my original digraph had some more non-adjacent pairs that will help us to take care of something which is crossing. Which are those non-adjacent pairs? Look at any arc if you had here. Okay, look at any vertex here. Look at any vertex here. Suppose I have some vertex here. Okay, what is the meaning of those vertex? What is this guy doing? Look, look at any directed cycle that crosses both sides, right? Now you notice that any directed cycle must contain, look, if I delete U, can you have a directed cycle? No. No, you can have, no, like this. You can go from here to here.
No, cannot do.
Why?
Induced.
Why?
Induced path.
Where? What is induced path? Induced paths of whom?
This U is a middle vertex of some induced path.
There's nothing. I have like, we have to look. Okay. But there are, but like whatever it happens, whatever that happens, where it will come? Look at any directed cycle. I'm telling you that any directed cycle must pass through the rest to come here. Look, if this vertex did not exist, is there a directed cycle in this digraph? If this set of vertices did not exist, do you have a directed cycle in this digraph? A directed cycle that starts from here, has to go from here, has to go from here, because that's the only way he can reach, and there's no way to reach back. Because there are no, remember, this do not exist because it's a triangle free digraph. In a triangle free digraph, I cannot have an arc from an out neighbor to an in neighbor, okay? And if you are going to use this, I'm going to pay for you by showing a induced path passing through you where there's some middle first will be there, don't worry, that's all that I'm saying, okay? Okay, so that's the whole goal, okay? So let's try to show that formally, it's just 2-line argument, okay? After that it is not much, okay? Okay. Okay, so I can say the following thing, no? Delta of D is at least delta of D1 plus delta of D2. This is true because and non-adjacent pairs in graph induced on this is also non-adjacent pairs before, right? So this statement is true because they are vertex disjoint, okay? Now what I am saying to you, now look at any induced path what happened?
I think it ended.
Okay, I think they okay. So now I want to say look at any induced path x u y of length 3. It is an induced path where u is the middle vertex. Where is x goes? Where is x? In I of, it has to be in, and where is y? In okay, which implies that x is in the vertex set of D1, y is in a vertex set of D2. Okay. So how many such paths are there? As many as non-adjacent xy pairs are. Look at here. It is pick up any x here, pick up any y here, okay, and if they are non-adjacent, then you are going to get an induced path. That's all that I'm saying. Okay. So I'm saying middle of P, okay, middle of P is the equal to number of pairs x comma y, x in of u and y in out of u and x and y non-adjacent, being non-adjacent. Is that correct? Is that statement fine? Okay. But what does that implies? Right? So, how much non-adjacent pairs are there? Plus, we can add something, no? Plus mid of u. Look, now we are only talking about non-adjacent pairs this side. I am saying to you, look at any non-adjacent pairs here, that is going to contribute to the middle of u. So, how many non-adjacent pairs you at least have? At least as many as middle of u. Right? Because every different non-adjacent pairs contributes, makes you different P. Okay. So now I can say is the following. Right? That is the lower bound from here, but those pairs are different from the new pairs that we have just created, which is equal to Middle of u. What is the meaning of middle of u? Middle of u is at least, okay, so is that fine? But they are at most first of u, we will use that fact. Okay, so now let me create some. Okay, so this is all that I wanted to do at this point of time. Now let me create a feedback arc set. So what I'm going to create feedback arc set, I said okay fine, because of induction hypothesis this statement holds. Okay, so you find a feedback arc set, say S1 and S2. S1 is a feedback arc set in D1, it is a feedback arc set in D2. Okay, we have found, and by induction hypothesis they are less than equal to this we know. Now I want to create some more things. Okay, now what I am going to do, okay, so now let F equal to pair of arcs x here, y here, every arc F equal to x, y, where is x? X is in out of u and y is in remaining of u. All these guys, okay, all these guys, okay. My claim is S1 union S2 union F is a feedback arc set. That's my claim. Why? We argued this before. Look at any cycle that contains, look at, we are talking about cycles, look at this portion, right? Look at this portion. Did I not, what did I define D1 as?
I of u union R of u.
But did I use u also somewhere? No, I did not use u. Yeah, it's fine. Okay, so there is no directed cycle here. Okay, so it is like this. Okay, it does not contain u, the way at least I have defined. Okay. Okay, so there is no directed cycle contained inside here. There is no directed cycle contained inside here. But so what are the other directed cycle that must contain? That every other directed cycle must contain the vertex u. Look at in my digraph. If it does not contain u, it means it is either contained here or contained here. Is that statement true? No. Because I could start from here, go directly to O of u, come here, go back. Okay, that's fine. But let's not worry about it. But those arcs are counted where? What are those arcs? F, F, F. What is F? X here, Y is in the remaining. Any arc that starts in out of u and goes into this, I took all such arcs, right? Now you can't have a cycle, right? Or you, even if you had used u, any cycle that you must come here, you go here, you can't go back without this. You have every cycle must go via rest of u. If I delete this vertex, you do not have any cycle in this directed graph. If I deleted cycle, so basically it says every directed cycle must contain a vertex in y, right? And it contains a vertex from here, it contains a vertex from here, right? So, but now what you did, you disconnected all this green arc. No way you can reach here, you're dead. You get my point? So after I deleted this arc, look at this partition. All the arcs are going from forward. There are no backward arcs. If there are no backward arcs, you cannot have a cycle going both sides. That's it. Okay, so this is fine. What is the size of F?
Can't there be cycle in only RU?
Only in?
RD.
You can,
That will be
but that's covered in D1, no? Are there class now? What class? At what time?
11.
Okay. I'll be just done in 2 minutes. Okay. Now let's bound F. Okay. What is the size of F?
First.
Every arc there contributes to first of u. Because look at you, you go here, you come here, right? You come here. Because these are non-neighbors, this is going to contribute to first of u. Right? Okay. So what is the size of S1 union S2 union F is upper bounded by size of S1, size of S2, size of F, which is less than equal to, what is this? D1. What is this? Plus first of u. But what is first of u? Is less than equal to middle of u by our choice. So this is less than equal to which is less than equal to delta D. We are done. It's a nice proof. That's it.